The ambiguous case is a complex phenomenon that arises in trigonometry when you have a question and in the question you are given the side, and non-contained angle of a triangle. So, for example, you are given the side, and a non-contained angle. So what I mean by non-contained angle, that means an angle that is not between the two given sides. So you're provided a value for A, you are provided a value for C, and you are provided a value for capital A or angle A. You do not have angle B given to you in the question. In this situation, there are two possible triangles that can arise. You can have this obtuse angled triangle, or potentially, if you are given side, non-contained angle, and not this side right here, you can also have an acute angled triangle that forms. So the ambiguous case arises if given side, angle in a question, and if it meets the following criteria. If the given side A is larger than C times the sine of angle A, as well as A being less than C, you have ambiguous case. So these are the two conditions that have to arise in side, angle for ambiguous case to happen. And that means two possible triangles. And that goes back to the actual term ambiguous. It just means there's not enough information to narrow down how many possible triangles exist with the given information. So we're going to go ahead and look at an example in which we are given insufficient information to know how many possible triangles exist. This question asks us to solve for triangle ABC, where angle A is 35 degrees. The side opposite to angle A is 10.2 centimeters. And the other side in the question is given as 15.1 centimeters right here. And so as you can see here, I don't have that bottom side. What I do have is I have side, and non-contained angle, which means I have to check to see if this is a situation in which we have ambiguous case. Okay, so by doing so, I have to check if this right here is greater than 15.1 centimeters times the sine of 35. So I have to check, does 10.2 centimeters, is that a greater value than 15.1 times sine 35? Okay, so the opposite side right here, is that greater than the other given side times the angle provided? And so we check, putting this into our calculator, 10.2 is in fact greater than 15.1 times sine 35. The other thing we need to check is the side opposite to the angle, is that less than the other given side? So that's the other check we need to do. Is 10.2 less than the other given side. And this is in fact the case. So therefore we have an ambiguous case scenario, and therefore two triangles are possible. So as you can see, we have this possible triangle right here, but we also have this possible triangle. This is my acute one. We also have an obtuse angled triangle as follows, where A is equal to 10.2, B is equal to 15.1, and side A right there is equal to 35 degrees. But this is the other possibility. So what I have to do now is I actually have to solve for both possibilities, because it asked me to solve for triangle ABC, but given these conditions, there are two possibilities for ABC. So what I'm going to do is I'm going to first solve for this triangle right here, and I'm going to do so using the sine law. So I'm going to go ahead and write that right now. As you can see here, I use the sine law, which says that sine B over side B is equal to sine 35 over 10.2 right there. And so I multiplied both sides by 15.1 to eliminate the 15.1 in the denominator here. Then I took the inverse sine of both sides to eliminate the sine right here. And I arrived that angle B right here is equal to 58.1 degrees. So that allows me to solve for angle C using the interior angles of a triangle. And angle C there should be 86.9 degrees. Again, that's an approximate value because angle B there is, is an approximate value right there. So that means this is 86.9. And then I can do sine law once again to solve for side C right here. And so side C is just found using that sine law right there. And that is equal to approximately 17.6. Okay, and so that was found using sine law once again. So sine of 86.9 over C, sine of 35 degrees over 10.2, and isolating for C, we get 17.6. All right, so now I've effectively solved for that one triangle. But how can I solve for this other triangle right here? Because this other triangle also exists. So I will do effectively the same thing, but what I can do to make things a little bit easier for myself is I can think about this triangle right here existing on top of this triangle right here. So I'll put that triangle basically on top of the other possible triangle, which I'm now drawing in red. Right there. And so as a result, remember that this side is 10.2 centimeters, which means this side is also 10.2 centimeters in this triangle right here. We can see that. That's 10.2, and that was also 10.2 right there. That's 35 degrees. So here I have A, B, and C. And what I'm going to do is I'm actually going to call this one right here B prime and C prime because they are different than this triangle right here. Having an isosceles triangle over here means that if this was 58.1 from this question right here, then that means that this angle right here is 58.1 degrees, which means that B prime in my second possible triangle is just equal to 180 degrees minus 58.1 degrees. So angle B prime is actually equal to 121.9 degrees. Again, I'm going to put a little dot over there because 58.1 was approximated. So this right here, that's equal to 121.9. That angle B prime. And angle C prime now can be found by doing 180 degrees minus 121.9 degrees minus 35 degrees. And so angle C prime is equal to 23.1. So this right there is equal to 23.1 degrees. Okay, I've solved all my angles. Now what I'm going to do is, and I know that this side right here is B is equal to 15.1 centimeters. So now I just need to solve for side AB. And I'm going to solve for side AB prime, this side right here, by doing side AB prime over sine 23.1 degrees is equal to, and then I can choose whichever I want. So I'm going to say here, okay, well, 10.2 centimeters over sine of 35. And then rearranging, I can find AB prime using Sine Law. And I get approximately 7.0 centimeters. So now I've actually solved for this other possible triangle. That was 7.0 centimeters. That's 121.9 degrees. This one right here is 23.1 degrees. And I have all my sides, all my angles, and again, that was achieved for this second triangle right here by placing this second triangle on top of the triangle I already solved and using the properties of an isosceles triangle.